Section 1.8, Proof Methods and Strategy. So in the last section, we went over some basic proof methods, and here we're going to go over some more advanced techniques and just some other tricks, some other things we can use to prove things. And so the first one that jumps out is proof by cases. And don't be thrown by the notation we're using here. We're saying if we're trying to prove something called P, and P can be broken up into, case P1 or P2 or P3, then a proof by cases is going to just prove each individual case and then draw a conclusion from that. So let's see a quick example. If n is an integer, then n squared is greater than or equal to n. And what you'll see a lot of times is you're thinking, okay, well, what are the cases I need to go over here? Well, n is an integer, and integers tend to come in three different types. There are three cases, they're kind of naturally formed when you're talking about the integers. They can be 0, they can be negative, they can be positive. So let's look at the 0 case first. It's easiest. Reading left to right here, if I take n squared, in this case n squared is 0, and I square it, I get 0. 0 is greater than or equal to 0, which is also equal to n. So I've shown that n squared is greater than or equal to n. So the theorem holds. Case 2, I want to apologize a little bit. This one's just kind of hard to read. So the assumption is n is greater than or equal to 1. And a lot of times after we make that assumption, we then move on, and I start with the left-hand side and I do these transformations, but this is going to look very different to us. I'm going to start with that n is greater than or equal to 1 assumption. So that greater than or equal to symbol is part of the proposition that I'm starting with. And I'm going to do that because I'm going to take that true statement that n, in fact, is greater than or equal to 1, at least for this case, and I'm going to multiply both sides by n. And that will get me to n squared is greater than or equal to n. The theorem holds. Final case, what if n is a negative integer? Well, here we're going to use the idea that if you take a negative number and square it, you get something that's 0 or positive. So I can say, well, if I know that little snippet, I can then say n squared has got to be greater than or equal to 0. The 0 is then strictly greater than negative 1, and by assumption, negative 1 is greater than or equal to n. So I've again proven my theorem. Next, we have an exhaustive proof. This is a proof where each case is a single example. So that is not what happened in the last case. While the case n equals 0 was one example, n was 0, the case n is a positive integer was many, many cases, right? Infinitely many cases. So we're going to switch gears here and look at a very different type of thing that we want to prove. Let's check out the min function. So we have this min function, and it only takes 2 arguments. So the debate we're having is, do I get the same answer if I take the minimum of A, and then the second object is the minimum of BC? So the first, when I run this as a chunk of code, I would take the min of BC, then take the min of A and the result. Is that the same thing as if I take the minimum of first run min AB, then additional input C? And so here the order is very much, it's kind of the whole thing that's in debate here, right? Will I get the same thing based on the order? There are 6 ways to order A, B, and C. So I get 6 cases, and each one of these cases is exactly a single example. So let's assume A is greater than B, which is, or sorry, greater than or equal to B, which is greater than or equal to C. Start with the left-hand side, that is min A, min BC. When I run minimum of BC, as by the assumption B is greater than or equal to C, I get C. Then when I run minimum of AC, I get C. Run it again for the right-hand side of the theorem, and I also get C. So in this case, I get the same result. In other words, the order doesn't matter. The left side is equal to the right side. We'll come back to this idea quite a bit later on in the class, but just remember that what's in question here is this equal sign, right? Is it true that min A, min B, C is equal to min A, B, C? The other cases aren't really worth looking at here. I have them listed. There's this little shuffle you have to do with your inequality signs. Don't get too caught in the weeds on that. That's not the point of this example. It's just to say, hey, look, if I want to do this, I'm going to have to break it down into precisely these 6 cases, and each one is only one example I'm literally running through. Which brings us to without loss of generality. So without loss of generality means that only one case needs to be provided explicitly because the remaining cases use the same argument. Be really careful here. People tend to overuse without loss of generality. They say it applies when it doesn't. So none of the previous examples I had was it without loss of generality. So you might be thinking, oh, well, without loss of generality definitely applied to that last example. No. That was the whole thing we were trying to show, is that there was no loss of generality with left and right, that you could shuffle around the order. Compare that to this example. If x and y are integers of opposite parity, then 5x plus 5y is odd. Now, we'll talk about opposite parity in just a second, but 5x plus 5y, remember that the letters here, x and y, they're just names for the variables. And we could literally swap the x and the y in this statement, and it wouldn't change what's being written here, right? 5y plus 5x is exactly the same as 5x plus 5y. And so suppose x and y are of opposite parity. What does it mean to be of opposite parity? Well, it means one is odd and the other is even. So if you just stopped right here, you'd have to do 2 cases. That is, let x be even, y be odd, and then the next one do y even, x odd. And maybe it's worth doing that once to see what it looks like without before we do the without loss of generality. But what you'll notice is that those 2 proofs are literally the same, only one of them swaps out x and y. So the only thing that's different about them is what you called the 2 variables, and that doesn't matter. So without loss of generality, we can say suppose x is odd and y is even. We're claiming that the argument would be exactly the same if we swapped the odd one and the even one. We know from our definition of odd and even numbers, that means that there exists a k1, k2, where x being the odd one could then be rewritten as 2k1 plus 1. Y being the even one can be written as 2k2. Substitute, factor, and you see that we can write this in the form of an odd number, 2 times an integer plus 1. So therefore we conclude that 5x plus 5y is odd. So if you want to prove there exists an x in the domain such that p of x is true, it's called an existence proof generally. Right? The general case is just called an existence proof. A constructive proof finds an element A in the domain and shows that it's true. So it's kind of like, this is the closest you get to being able to say, hey, there's an element that makes this true. I'm going to show you because I found it. Then there are non-constructive proofs. And we'll put that to the side. I know this definition is kind of lame. We say, hey, a non-constructive proof is one that is not a constructive proof. But again, set that to the side. We've seen existence proofs before. Let's do a really simple one. There is a positive integer that is the sum of the positive integers less than it. Proof, really simple, because I found it. It's 3. 3 is equal to the sum of integers, positive integers, sorry, less than it. 1 plus 2. Nothing fancy there, right? You say, hey, it exists, and you go find it. The non-constructive one is way more interesting, and I think this might be one of the more interesting examples we do in the entirety of the course. So let's say there exist irrational numbers, x and y, so they're both going to be irrational, and it's going to be such that when I take x and I raise it to the power of y, I get a rational number. Now the difficulty here is that it's hard to work with irrational numbers. It's kind of like the constructive and non-constructive proofs. We know what a rational number looks like. And then for irrational number, we just say, okay, but not that thing. So how are we going to show this? How are we going to find this? Well, we're going to work from what we do know, which is that the square root of 2 is an irrational number. So I'll present to you two cases. This is just a clever little trick. We're going to look at the square root of 2 raised to the square root of 2. Case 1, the square root of 2 raised to root 2 is a rational number. If that is the case, we're done. We did a constructive proof in that we found the example. Now bear with me, it's not a constructive proof because we didn't prove that this was rational. Just if this case were true, there's nothing to be shown here, right? Root 2 is irrational, so we'd have an irrational raised to an irrational, and the conclusion is, hey, that's a rational number by assumption. There's just nothing to show here. So where it gets interesting is case 2. Suppose root 2 raised to the root 2 is irrational. If that's the case, then I can let x be the irrational number root 2, which is irrational by assumption, and y will be the irrational root 2, which we know is just an irrational number. If these are my two numbers, then x raised to the y reduces all the way to 2, which is a rational number. Now the interesting thing here is I don't know which one of these is true. And if you take a second, think about it, that's kind of miraculous, right? I've shown you that this idea has to be true, but I didn't ever go out and find it. Is it root 2 to the root 2? Or is it root 2 as one of the numbers and then root 2? I don't know if it's case 1 or case 2. And so I didn't construct the example for you. I've just kind of shown, well, it has to be out there. And that's what makes this a non-constructive proof and a really interesting example, right? Again, I've shown that it has to be case 1 or case 2, and both of them give the result. But at the end of this process, I don't know if case 1 is the rational one or if case 2 is providing the rational one. It doesn't matter though, because they both end with the result that we found an irrational raised to an irrational that is a rational number. So a non-constructive proof. I didn't find the example that made it true.